Hi everybody, my name is Scott Fleming. I'm from the Space Telescope Science Institute located in Baltimore, Maryland in the United States. I'm also a member of the Astronomy team, one of the many teams working on sonification in astronomy. I've been asked to give an overview of what we call one-dimensional data in astronomy and an overview of some of the groups who are working on ways to sonify it, especially for research purposes. To describe myself, I'm a middle-aged white male. I have glasses, dark brown hair, and a full beard. So let's get into the talk here. First thing I should probably do is explain what we mean by one-dimensional data. Now, I did say we're talking about one-dimensional data in astronomy, but by no means is one-dimensional data unique to astronomy. Basically, what I'm referring to is some value that changes along with some other value. So some examples outside of astronomy that we might be familiar with may include the price of stocks each day over the last year. Or a funny example is how far I can run after eating a given number of sandwiches. And as a spoiler alert, what we might expect is that will go down the more sandwiches that I eat. Some examples in astronomy include measuring the brightness of an object over time. We refer to that as a light curve. Another example might be measuring the intensity of light at different frequencies. One example of this is prisms, when light go through that and create rainbows. In astronomy, we call this a spectrum. And these are the two most common types of one-dimensional data in astronomy: light curves and spectra. Why do we want to study light curves in astronomy? Well, when an object changes in brightness, we can use that to learn more about the object itself. So some examples are we can measure how fast an asteroid is spinning by watching how its brightness changes over time as it rotates different parts of it in and out of our view. Another example might be pulsations in stars, where we can model and measure how stars change in brightness over time, and that can indicate changes in the star's physics or internal structure or atmosphere. Another example are changes in brightness that can be used about other types of objects. So, for example, a planet that's orbiting a distant star will sometimes block the light of its host star if it happens to cross in front of our line of sight and the star it's orbiting. Another example would be bursts of light that we see after a black hole destroys a star that may have gotten too close and got absorbed into the black hole in an explosive event. So we can use changes in brightness over time to learn about objects themselves, or in the latter examples, other objects that might be interacting with the thing that's giving off the light itself. Why do we want to study spectra? Well, in this case, what we're really looking for is how each element or molecule emits or absorbs at very specific sets of frequencies. So we refer to these things as chemical fingerprints. Basically, every element or molecule has very specific frequencies at which, depending on which of its electrons are going from which state to another, will either absorb or emit, depending on the physical conditions, at very specific frequencies. And so if you can measure those frequencies and you know the physics that go into atoms and molecules, we can use these chemical fingerprints or spectra to figure out what sort of elements or molecules might be contributing to that particular absorption or emission, and some properties about the material. So the presence or absence of these specific frequencies can tell us things like the chemical composition of dust, or planetary atmospheres, or the stars themselves. Another example is if we find a set of these chemical fingerprints, a set of these spectral lines, but they're shifted from where they're supposed to be, we can use this measurement to help us understand the velocity of the material, whether it's moving toward or away from us, and how fast it is moving toward or away from us. And then for many objects, the distribution of these light intensities across a wide spectrum can be used to measure other properties like their temperatures or sometimes even their ages when we combine the intensity distributions, these spectra, with models and our understanding of astrophysics. So what's a common approach to sonifying one-dimensional data? Well, the default is sort of straightforward conceptually, since we have two variables, two sets of measurements. We can sort of make each measurement its own note, and then we can assign the thing that changes to a particular pitch, where if it increases, for example, if brightness increases, we can make a sonification rise in pitch, and if the brightness decreases, we can make the sonification pitch fall. And then the thing that we're tracking, so the brightness over time, or the intensity of light as a function of frequency, or the distance I've run after the number of sandwiches I ate, that the thing that we're tracking things by, date, frequency, number of sandwiches, can correspond to the time in our audio file. So it's relatively straightforward to take these two things and map them to pitch and time, which gives you a sound. But there's a lot of complications on the details, so you have to make some choices about your note spacing, the pitch scaling, the note duration, even the specific types of sound that you use. And at this point, it's probably worth mentioning that there are very specific types of sonification. The sonification for a lot of the packages we'll be talking about in this presentation are primarily designed either in part or fully to support research, which has similar but also different needs and requirements from sonifications that might be primarily focused on outreach or education, for example. And so there's additional considerations when sonifying data for research or for specific educational goals, where the sonification need to represent the data in an authentic way, as opposed to other uses where sonification, the primary goal might be to entertain or to teach certain concepts without having to worry as much about some of the complications of representing the data as they are. So at this point, I'd like to show an example of one of the most common uses for light curves these days, and that is to look for for objects that are transiting or crossing in front of the host star. So I'm going to play a sonification, and I am showing a plot of something that looks like the letter U, if you trace that out in your mind. We have a bunch of wiggly measurements with some with some variation. And then about halfway through, we're going to see an object cross in front of our line of sight and block some of the light from the host star, which will cause a steady and relatively sharp drop in the total brightness of the object. And then when the object is fully in front of the star and marching its way across, it's going to more or less hang out at some lower flux value until it begins to leave and cross the other side of the star out of our field of view, in which case the brightness will go back to its normal constant value with a little bit of noise there. And so I'm going to play what a sonification of this might sound like, and see if you can listen and hear the shape of the transit as I described it just now. So hopefully that sonification, when you sort of listen to it and then compare it with your mental picture was when I described what a transit looked like, match, at least at some level. And we'll go into some more specifics about what are important for these sorts of light curves, because there's other activities in the workshop that will refer to transits in particular. So what are some of the most important properties of a transit? So There's a couple of primary key parts of a transit we're looking for. And essentially the reason we're doing is that the shape of the transit, or in the case of sonification, the sound of the transit, can tell us a lot about the object. The amount of light that's blocked, which we refer to as depth, is related to the size of the object that's blocking the host star compared to the star itself. So you may imagine that for a given size star, a smaller object will block less of the light than a bigger object. And that means that the depth, or the amount of light that's blocked, is directly proportional to the size of the object blocking it relative to the star itself. Another important parameter we look for is called duration, and this is a measurement of how long the transit lasts. And then the third most important measurement is how often does the transit repeat itself, and that's referred to as the period. Now these two things, the duration, how long the transit, each individual transit lasts, and the period, how often the transits happen, combined tell us information about the orbital property of the planet. And so you can see already with these three relatively basic measurements, the depth, the duration, and the period, we already are starting to get some clues as to what the size of the object might be, and some information about the orbital properties of the planet or whatever else is orbiting this particular star. Additional modeling can tell us even more information. So, for example, the detailed shape of the actual transit can tell us a lot more information about both the star that the object's crossing and the object itself. So some of the things we look for here are shapes, whether the transit looks like the letter U or the letter V with sharper edges and shorter base there, or even something that's very square, like the bottom of a square where you have very, very sharp sides and a very constant bottom. The details of these shapes can be used with models to help us understand better the properties of the objects involved. And much the same way, sonifications that can tell us differences between those shapes can be used to help understand the data in a very similar way, or even a very complementary way with other techniques. I'm going to show you one more example. There's actually quite a number of different types of sonifications for different types of changes in object brightnesses. I could give a whole presentation just on those, but in the interest of time, I'll just give you one more very different example. And this is a sonification of a measurement of a particular star's brightness over time, again. But unlike the transit where an object is orbiting it, this star is essentially by itself and changing brightness by itself due to some instabilities in the star itself. Now these instabilities are causing the star to wobble. I like to use the analogy of a bowl of jello that might have been hit, where you're sort of wobbling and wiggling around a little bit. And as these stars wobble and wiggle, the size of the star changes in different ways, which means the brightness of the star changes in different ways. And if we measure them very carefully, we can record those brightness changes and then use, once again, models and our understanding of how stars work to be able to provide very detailed measurements of the internal structure of the star, something we would normally never be able to get access to. And a good analogy here is actually earthquakes. So we are unable to visit the center of the Earth, except for in science fiction movies, but through seismology, we can send sound waves or other waves through the Earth and then record them coming back to us to understand properties of the interior of the Earth that we would normally not have access to. And in much the same way, we can use these pulsations to understand properties of stars that we'd never be able to actually otherwise learn about. And so I'm going to play this sonification, but first I'll describe it. And so what we have here is a set of brightnesses that are varying quite a bit, actually, quite rapidly. And you may or may not hear hints or evidence of different periodicities, we'll call them, in the sonification. So I'm going to play this sound right now and see if you can figure out what you might look like as a mental picture. To me, it almost sounds a little bit like someone doing a record scratch or something like that. And if I played a longer data set, in many of these cases, you actually do find that there are stable, or at least somewhat stable, frequencies within the various pulsations, and we actually use those frequencies to better understand the stars themselves. So it's a pretty interesting phenomenon that we're using quite a lot these days to understand stellar astrophysics. So I'm going to include one final sonification example of 1D data, and in this case I'm not going to talk about light curves, I'll instead talk about spectra. And I want to give credit, I'm using a sonification example provided by Gary Ferran and Jeff Hannum and their software application called Starsound that they use for astrophysics research of spectra. What I want to show as an example is a sonification of a galaxy. So we are measuring intensity of light at different frequencies, and the description here is, the best analogy I have is to imagine a set of stairs. So the first shape that is this spectrum is made out of, you could think of as like 2 stairs. You have one level and then you have another level up above it. Now in these stairs there are also some cracks, and those cracks have different depths. Some of them are pretty shallow, some of them are pretty deep and broad. Those cracks in the stairs represent those fingerprints I was talking about. So these are specific frequencies that are having some of their light absorbed by material that have specific molecules or elements that are responsible for those different cracks. And then there's one other surprise, which is a splinter. So there is an emission line. That's the opposite phenomenon, where instead of having a particular element or molecule absorb at different frequencies, there are some situations where those particular elements and molecules might emit or provide or produce extra intensity at a particular frequency. And in this example, we have a one emission line coming from a particular atomic transition, so a particular transition where a electron is going from one energy level to the other in hydrogen. So this is a very famous astronomy line that's caused by hydrogen atoms. And see if you can listen to all 3 things. So there's a step function, like a step plateau overall. Within that step, there is a number of cracks in our stair that represents the absorption of different elements. And then at some point that I won't tell you ahead of time, there's going to be a splinter or a sharp feature sticking out, and that's that special hydrogen emission line. So let's listen to the sound now, see if we can hear all those things. So there's a lot going on there. I'm going to play it again, especially because there's those, unlike some of those other light curves, there's actually a number of different features going on. But to describe even better, the first step of the overall stair pattern happens pretty quickly, maybe about 10 or 15% of the way through. There's a step up to our second step. You'll start hearing some of those splinters or absorption lines pretty soon after you get on that first step, and then about just a little shy of halfway through, maybe about 40% of the way in, you'll hear a really short and sharp increase, and that's that splinter, the piece of our wood step sticking up, and that's the emission line from that particular hydrogen atom. So let's play that sound again and see if you can hear some more of those features now that you have another description. So spectra are inherently very feature-rich, and that's why sonifications can provide not only accessibility, but important additional way of analyzing the data sets. And again, I'd like to thank the Starsound team, in particular Jeff Hannum and Gary Ferran, for providing this material. All right, so let's move on. The next thing I'm going to do is try to highlight some of the sonification tools that I'm aware of that are actively working on one-dimensional sonification in astronomy. This is not necessarily a complete list, but I thought it would be helpful to sort of do one slide, very short overviews. I'm not going to do any of them justice, but to give you a little flavor of some of the work that's going on already. And there'll be more information on these available, or you can also reach me as well, and I can provide references and links. But the first piece of software I wanted to go over is something called Astronomy. So that's the piece of software that I work on with another team at Space Telescope Science Institute and in collaboration with Glass Education. This is a piece of software written in Python. It is open source, and it runs through the command line. We do not have a graphical user interface yet associated with Astronomy. And the goal of our project is to provide sonification for research purposes from all the different astronomical data that we have in the archives at Space Telescope, which includes a number of NASA missions, especially space-based telescopes. The software, as of now, is designed for light curves, as we've talked about toward the beginning of the talk, but there's nothing technically limiting you from being able to use this to sonify spectra. It's just that there was no special consideration given so far for specific needs of spectral analysis with our tool. Our tool is configurable. You can change lots of parameters through the software, including things like the note spacing, the note duration, the pitch mapping. And the software can output sonification as a WAV file if you want to save it or use it with other audio programs, or you can play the sound directly in interactive interfaces called Jupyter Notebooks, which are used very commonly in Python software, although unfortunately are themselves not natively very accessible with screen readers, but there are ways to convert them into HTML that make them accessible again, which is what our team does. Another example is Starsound. You already heard an example actually from the Spectrum example I played just a little while ago. I would like to let everybody know a reminder that the Starsound team is providing a presentation of their software at the workshop, so I would definitely encourage you to spend time watching their presentation. Their software is built for Mac OS. It's available as a precompiled binary, and it does have a graphical user interface. The software is highly customizable. There's multiple modules available, so you can assign different notes and sounds to different, essentially, channels or data sets, data parameters. The input data and the sonification parameters can be controlled by an ASCII configuration file, which is useful for all users, but you can also configure the sonification parameters and the input data from the user interface as well if you would like to do that. And it's pretty generic. It can handle pretty much any type of data that you can provide it in ASCII text format. It's pretty agnostic about whether it uses light curves or spectra, and it does have support for MIDI input and output as well. Another example is software called SonyPi, SONI-PY. There is actually another package called SonyPi without the dash, which is different. I'm talking about Sony-Pi. This is an open source Python package. It's pretty similar to Astronomy actually in a lot of ways, although not all of the ways. Its primary goal is to enable citizen science, so allowing members of the public to be able to help study and classify stellar explosions, which we call supernovae, using sound. It can sonify other light curves as well, though it doesn't have to be supernova, and there's nothing stopping you from giving it spectra, although it's not the primary intent of the tool. And like Astronomy, it is configurable. You can change the pitch mapping and the timing between the notes, but the configuration parameters differ from how they're specified between the two tools. Another example is the saunauno, and I'd like to give everyone another reminder that this team is also presenting at the workshop. I would recommend and highly recommend that you listen to their presentation on their software. Their software is open source and written in Python as well. This is a pretty common theme. Python is very popular software language in astronomy. It does include a graphical user interface. The primary goal is to enable science and data exploration, and it can do two things actually. It can plot and sonify the data in the singular package with built-in plot visualizations as well as sonification options. You can input your data as text tables, and it saves the plot data as text and the sound data as well. And similar to Starsound, it wasn't really designed for a specific science case or subfield within astronomy, so it's pretty generic and fairly agnostic about what type of data you give it. Another example in the spectral regime is something called Sonification Spec. So this is a package that's written in a different programming language called IDL, although the team is working on a Python version that will be what they will be giving to the public when it's ready. And it does include a graphical user interface. In this case, the software package is designed to analyze spectra as opposed to some of those previous ones that were designed to study light curves. It takes as input either text files or what's called FITS files, which is a format of data that's pretty popular in astronomy. And the output can be sound in a number of different formats. It can plot, like the saunauno, it can both plot the data and play the sonification in the one package with some pre-built sort of visualization tools. And it also can compare two different spectra together, which is a somewhat unique at least advertised feature for a lot of the sonification tools I'm aware of. And they're actively working on ways to configure their sonification, which is an area of active development right now. And then the very last piece of software I'm going to talk about is called Quasar Spectroscopy Sound, or QSS. This is open source software. It's written in C++, not in Python, and includes a compiled binary, so you can get it running on your machines, hopefully pretty quickly. And it does rely on a graphical user interface. Unlike the previous tool, which was designed to study spectra as a whole, this tool is actually designed to focus on individual spectral features. So if you remember those chemical fingerprints, those specific frequencies that might be absorbing or emitting light at very specific frequencies, well, this tool is really designed to really drill and zoom in on those individual features and study things like their shape, a little closer to like what we're doing with those transits. How deep is it? Is it symmetric or asymmetric? And other properties of each of the individual spectral features. And you can configure the sonification from within their user interface. And what's interesting with this tool is that a lot of the sonification configuration is sort of tied to the physics of these spectral features. So instead of sort of allowing you to configure sonification parameters based on sort of pure sound, they do, in my opinion at least, a more direct job of tying properties of their sonification to the things we're trying to measure or understand about the spectral features, which is an interesting approach to take. So that was a whirlwind tour of a number of different packages. I want to go through and just make some final comments on what I think are some of the similarities, some of the differences, and then some open questions. So some of the similarities I found between all these different packages is that they're all open source or planning to be open source very soon, which is something that I think is very important, and I'm very proud of this community. I think that sort of goes hand in hand with the idea of accessibility in general. We want our software to be shared freely and to be able to have everybody contribute to it. All of these software packages allow you to configure the sound, which is also very important, not just for different users who may have different preferences or needs for how the sound is configured, the sonification is configured, but also the science itself, or even the objects themselves, will likely require the ability to configure the sonification on a need-by-need basis. And then at least the ones I've shown today, which was a little bit self-selecting, but I want to emphasize there's a lot of groups who are focusing on sonification for research purposes, which is an important part of the multi-step process of making astrophysics as a career more accessible. there's a lot of important work that has to happen in many, many areas and at many, many career stages, all the way down to the very beginnings of education. But a lot of the roles that some of the professional astronomers can play is to make sure that the ability to use data for research purposes or specific educational goals can have accessibility through sonification. And I think a lot of these tools are either making that a primary goal or one of their goals. Some of the differences I noticed, some of the packages focus primarily on getting it as a script, so something you can run from the command line or include as part of your own software, and others really had a heavy focus on graphical user interfaces, and a couple of them actually enabled both. I think that all of them were configurable, but almost none of them had exactly the same ways of configuring the sonifications. So there's really no standard in terms of how to specify your sonification parameters. And then some of these tools were really agnostic and generalized, where they just wanted to take data in a simple format and can sonify the data and let you configure it from there. And others had specific either science, sort of astronomy subdisciplines, whether it was tailor-made for light curves or spectra, or in some cases even very specific goals in mind, like analyzing the specific shapes of individual spectral features as opposed to being somewhat more generic. So there's a variety of different use cases within astronomy, even just within the tools I presented here. And then the last thing I want to talk about are some open questions. So some of the things that I didn't notice that were immediately apparent. Admittedly, I don't use all of these tools on a regular basis, but I think there wasn't a focus in any of these tools on how to really be able to handle measurement uncertainty in the sonifications. I'm sure all the teams have thought about it, and they may even have some examples working in their software tools, but it's a big area, I think, that can use a lot of exploration, is how do we convey in the sonifications sort of measurement uncertainty without impacting our ability to use the sound in other ways to understand what's happening with the data. Another question was scalability. So especially in modern astronomy, there are lots of data sets that have thousands or tens of thousands or even hundreds of thousands of data points, especially for light curve data sets. And so how do these sonification tools can they handle data with huge numbers of points without having to either make sonifications that take hours to play, which is obviously not going to be really feasible to use, especially for a large number of objects, or having data that plays so fast that it's hard to pick out some features that may happen halfway through the sonification. Another example I thought about was handling multiple data series in a single sonification. Now, there were a couple examples of tools that could handle, at least at some capacity, multiple data sets, but it's a pretty common use case in astronomy to be able to, for example, compare some models with the observed data. In that case, you have one data series that is the measurements and a separate different data series that represent something with the models that you're trying to compare against. Another example might be just comparing head-to-head, different data sets. Maybe it's two different data sets of the same object but taken at different times, or it could be different objects just comparing against each other. So how to handle multiple one-dimensional data sets in one sonification is an interesting area. And then the last thing is standardization. That's a big one, something that I'm sure all the teams have talked about. And it's an open question, I think, about whether it would be helpful, harmful, or neither to work on setting up some sort of consistent standards or templates for some basic sonification principles for one-dimensional data, even how to configure the tools. In some ways, being able to have these different tools and different data collections sonified in a familiar way can help people access the data in much the same way that standards help with other ways of accessing data. But at the same time, the need to be able to be flexible both for individual users and individual science cases and objects, is an important part of sonification, and it's not going to be an easy thing to answer, and I think it's going to be an important thing to continue to talk about with experts as we hopefully move towards increased ubiquity of sonification in astronomy for professional research purposes. So this was my introduction to one-dimensional data and sonification. I will provide links or references for all of these with the slide notes. And thank you for your attention, and I hope you enjoy the workshop.